Hi everyone, in this video we will see together how the thermal conductance correction works, why it's needed, and I want to start with explaining to you why it's needed. Well, first of all, we have to understand how our cantilever works. Well, maybe you already know we have a tip and we have two resistors. We have the resistor of the writer and the resistor of the reader. When we read, we use the signal of the reader, and the reading process is a process that uses the signal that's measured by the reader. So we measure the heat flux through the between the reader and the surface. So one thing that is important to keep in mind is that whenever we have some different materials or we have some particular topographies, this can introduce some artifacts in the image that we read because the thermal conductance will change. This is also true in case we pattern something. So if we remove a lot of polymer on our sample and we get closer and closer to the substrate, let's assume we have PPA on silicon, then the thermal conductance of the area where the polymer is being removed is going to be different from the area where the polymer is not removed. So this creates some ghost topographies or some artifacts in general. It's important to keep in mind that the reader is not really located where the tip is, so the ghost topography will be shifted by the distance that there is between the tip and the reader. To see a little bit more in detail the concept with images that I hope can help you understand a little bit more. What happens is that when we are doing our in contact read, in case we have, let's say, a topography with another material, let's say we have gold on top of silicon, this will create a convoluted signal where we measure the topography, but also we add the thermal conductance because the heat flux, let's say this is gold, is going to be higher in this area with respect to the other areas where we have silicon, for example. So what we do is that by the thermal conductance correction, we introduce an out of contact reader. So we need to have at least an upsampling factor of 2 when we introduce the thermal conductance correction. And this images only the thermal conductance and applies this correction on the reading that we do, so that we have a corrected topography. So hopefully we only read the topography on our surface. In general, we can have increased heat flux due to closer topography, for example, and due to material changes also, let's say we have silicon, gold, silicon, and in this case this introduces a ghost topography. It's also true whenever we just remove PPA, and this maybe is not so intuitive, but I would like to show it to you now with the NanoFrazor software. So I was just doing a reading of a structure that we see here. So we have a specific structure. It's very deep. We have in this case a sample with 200 nanometers of PPA roughly on top of silicon. And we see that here we have a depth that almost goes down to 200 nanometers. So here we have quite a lot of polymer. And here we almost have the silicon surface exposed. So the thermal conductance should also change quite a lot from here to here. So first of all, where do we find the thermal conductance correction? We find it here in the read parameters. And let's check it now and see what we can observe. So I start the pattern now. It's going to take 3 minutes. We can also make some consideration while this runs. So what do we expect to see? First of all, we expect to see something that looks like this topography that's a little bit shifted because, as we saw in this presentation, there is a shift. I mean, there is a distance between the tip and the reader. So as we are seeing this ghost topography here and here, then we should see a ghost topography in case we don't apply the thermal conductance correction, or we should see this signal in the thermal conductance analysis. So the thermal conductance is here, so we can also enable thermal conductance from this analysis panel, and we can already see that we are seeing quite a large shift in the thermal conductance. So this is correcting by almost 50 nanometers. And at the moment here, we're still not seeing anything because the tip is going across on top of the PPA surface, while the reader is already on top of the topography that's very deep. So this means that if we didn't have the thermal conductance correction activated, this will introduce some ghost image. So let's try to see if that's true. So we already see something, even though so now we're starting to see the real topography, but we see a sharp increase because of the remove the thermal conductance correction. So we see that here is where we stop the thermal conductance correction. Now I will check it again, just to confirm that we are indeed seeing this topography with the thermal conductance correction. So the signal measured by the reader through this additional scan that we add in air. So in general, in this case, we can really appreciate the thermal conductance correction because we see a shift of 45 nanometers because we have a very deep pattern, and the thermal conductance changes a lot on the surface because we're of course having the the conductivity of a polymer compared to the conductivity almost of the silicon that is almost exposed in these areas especially. And we can see, of course, that we see these two topographies with a shift. So indeed, we are having an effective use of this correction, which improves our reading and can also help in our our writing in case we're using, for example, a feedback. So I hope this can clear out some doubts about the thermal conductance correction, why it's useful and how it works. And I hope this will help you in making better reading and also better writing and understand better the NanoFrazor.